Nidhi Patel, and along with my classmates Naval and Siddharth, we conducted a mini project on analysis of amplitude modulation performance in communication system under various noise conditions using different modulating signal. We are the students of Sardar Patel Institute of Technology, and we are excited to walk you through our analysis and findings. We explored the behavior of amplitude modulation using sine, square, and sawtooth wave as modulating signals and analyzed their performance under different noise conditions at various signal to noise ratios, that is SNRs. So let's start by discussing the first part of our project where we focused on modulation and demodulation. We took the frequency of the modulating signal as 10 Hz while the carrier frequency is 250 Hz. To ensure proper sampling, we set the sampling frequency at 10 times the sum of the carrier and twice the bandwidth of the message signal. This setup ensures that our sample signal have sufficient resolution for modulation and demodulation analysis. After that, we generated three types of modulating signals, that is sine wave, square wave, and sawtooth wave. Each of the signals have unique properties that impact the behavior during modulation and demodulation. We can see them in the figure 1. Then we use the mod function to modulate the signal with a high frequency carrier, and we can see the modulated signal in figure 2. We introduce the noise at different SNR level 5, 10, 15, 20, 30 and 50 dB using the AWGN function, and then demodulated the signal using AMD mod. Now let's take a look how this signal behave at different SNR value. This is at 5, this is at 10, this is at 15, this is at 20, this is at 30, this is at 50. After finding out mean squared error between the original and demodulated signal was calculated, we found out that sine wave had a lowest MSE at all SNR value, indicating its reboost to noise, while square wave showed higher MSE, especially at lower SNRs due to the discontinuities and harmonic rich structure, while the sawtooth wave performed better than the square wave but not well as the sine wave. This finding emphasized that sine wave are optimal for amplitude modulation in noisy environments as they maintain high fidelity after demodulation. So, in practical communication system like amplitude modulation radio, these insights are crucial. In urban areas with high electromagnetic interfaces, maintaining the high SNR ensure clear signal reception. Our analysis highlights the importance of choosing the right type of modulating signal to enhance communication reliability. Part of our project, we analyzed the effect of three types of noises, that is uniform, impulse, and pink, on amplitude modulation signal. We wanted to see how each noise type impacts the modulated and demodulated signal at different signal to noise levels, that is 5, 10, 15, 20, 30 and 50 dB. Our primary goal was to observe signal degradation and quantify its using mean squared error analysis. We use three types of signal. First one is uniform signal. It's a random noise evenly distributed across the range of minus 0.5 to 0.5. The second one is impulse noise. It's a high amplitude spike that stimulate real world interfaces. And the third one is pink noise. It's a noise with a frequency spectrum where power density decreases with frequency, often used to stimulate environmental noises. We tested our AM signal with noise added at different SNR levels ranging from 5 to 50 dB. The lower SNR level 5 to 15 dB represent high noise environments leading to more signal distortion, while the higher SNR level 20 to 50 represented cleaner signals allowing better recovery of the original message. Now let's observe the uniform noise. At lower SNRs 5 to 15 dB, we observe significant distortion which led to high MSE value. At the SNR increases from 20 to 50, the demodulated signal improved, the MSE dropped. At 50 dB, the impact of uniform noise was minimal and the demodulated signal closely matched the original one. Here graphically we can clearly see that the MSE decreased steadily with increasing SNR, displaying a predictable noise behavior. Graphically this appeared as a smooth decline in MSE values as the SNR increased, demonstrating that the impact of uniform noise diminished at higher SNRs. Impulse noise. This noise type caused severe distortion at lower SNRs due to the high amplitude spikes. Even at higher SNR 20 to 50 dB, the signal showed residual distortion, resulting in higher MSE values compared to the uniform noise. Impulse noise is particularly damaging because of its unpredictable nature. Graphically, it is seen that impulse noise consistently resulted in higher MSE value, showing its severe impact on signal quality. Its erratic nature was reflected in the graphical analysis. Now let's take a look at the pink noise. At the lower SNRs, pink noise affected the signal more at lower frequencies, leading to moderate MSE values. As the SNR increased, the impact of pink noise lessened and the signal quality improved, with MSE decreasing significantly at higher SNRs. Here graphically we can clearly see that the MSE decreased steadily with increasing SNR, displaying a predictable noise behavior. Graphically this appeared as a smooth decline in MSE values as the SNR increased, demonstrating that the impact of uniform noise diminished at higher SNRs. Amplitude modulation under varying noise condition provided valuable insight into how different modulating signals and noise type impact signal quality and resilience. Through the analysis of sine square and sawtooth wave, we observed that the sine wave consistently offered the best performance, maintaining the lowest mean square error (MSE) across all the signals to noise ratio level, making them optimal for AM in noisy environment. The analysis of noise type, uniform, impulse, and pink noise also demonstrated that impulse noise has the most disruptive impact, especially at lower SNR. Look at some real-world application of the AM under noise condition. First is AM radio broadcasting. Understanding how different modulating signals and noise type affect signal quality helps improve AM radio performance, ensuring clear reception in urban and rural areas where interfaces entry varies. Second is emergency communication system. Knowledge of noise impact on AM can help in designing system that remains reliable under adverse condition, ensuring critical message reach people during national disasters or crisis. The third is aviation and marine communication. AM is frequently used in aviation and marine communication insights into handling impulse noises. Example from thunderstorms can enhance signal stability, ensuring uninterrupted communication with pilots and ship. And the last one is military and strategic communication. AM is used in some military communication system. Understanding noise effects allows for better signal transmission and reception, which is crucial for reliable, secure, and communication in the field.